A long, wet hiss, a soft click, and the stream of fuel dies like someone cut the cord. Gas beads cling to the tip, wobbling in that tiny moment between flow and stop. You lean in, thinking you messed up. It looks like a mistake. Today, we're uncovering why gas pump nozzles click off automatically, how a tiny pocket of vacuum inside the spout does the shutting, and why regulation and money quietly shape that choice. To understand why gas pump nozzles click off automatically, we first have to look at what happened before it. Filling a tank used to be a slow, hands-on chore. People poured from cans, eyed gauges, and wiped spills with rags. Spills were common, fires were a real danger, and every ounce lost at the pump meant money gone and fumes in the air. Inventors tried floats, manual shutoffs, even special funnels. Most early fixes were either too fiddly for attendants or too leaky for station owners. That pain, the cost, the risk, the cleanup, created pressure for something simple, reliable, and cheap. Most people think an electronic sensor or a clever computer tells the pump to stop. You picture a little eye in the nozzle that sees liquid and mutes the flow. That's neat, and it fits our modern instincts. If a problem exists, make it smart. The real trick inside the nozzle is mechanical and almost charming in its simplicity. Near the tip, there's a tiny hole called a sensing port, and that port links to a narrow tube that runs back into the handle. When fuel flows, air rushes through that port and down the tube, creating a small pressure difference, a tiny vacuum that keeps a diaphragm or lever pulled so the main valve stays open. When liquid arrives at the tip and blocks that sensing port, the airflow collapses, the vacuum vanishes, and the diaphragm lets the valve snap shut. In short, the nozzle listens to the air, not the liquid. If you like analogies, think of it like a straw and a traffic light at the same time. Covering the top of a straw changes the flow instantly, and that change flips the signal from green to red. Technical term, Venturi Effect. In other words, flowing fluid creates pressure changes that mechanical parts can read. The result is fast, power-free, and largely foolproof, until it isn't. But here's the weirdest part. That tiny sensing hole can be tricked. Angle the nozzle oddly, wedge it against a filler neck lip, or use a high-flow feed, and the airflow pattern can behave strangely. Sometimes the valve shuts too early. Sometimes it hesitates. Manufacturers spent years tweaking shapes and internal paths just to make that little vacuum behave consistently across cars and tank designs. That tiny sensitivity led to patents, shape changes, and constant small upgrades. So, why design a system that depends on a hairline vacuum and a hole you can accidentally hide? Because the dominant forces pushing the design were safety, cost, and regulation. A purely mechanical shutdown needs no electricity, has fewer failure modes, and is cheap to build and maintain. Station owners want something that works without daily fiddling. Regulators want a method that reduces spills and vapors without requiring expensive tech. Manufacturers want something they can mass produce and protect with patents. And this is where it gets interesting. Money and law did more than nudge nozzle shape. They shaped entire product lines. When air quality rules tightened, pumps had to reduce vapors at the point of refueling. That pushed makers to add jackets, seals, and extra plumbing to nozzles and hoses. Regulators and vehicle makers also introduced systems on cars to trap vapors during refueling, which meant pumps had to play nicely with two different approaches. The result? Stations paid for retrofits, manufacturers raced to patent improvements, and regulators, notably the EPA, set standards that nudged designs toward capture and shutoff rather than electronic automation. Who benefits? Consumers get fewer spills and cleaner air. Who pays? Stations and manufacturers bear most retrofit costs, and taxpayers pay through regulation and enforcement. But here's where it gets complicated. Some regions required sealed systems at the pump. Other regions relied on car-based systems, and where both existed, the two could conflict. That created a patchwork. A nozzle that behaved beautifully in one state could misbehave in another because the car's tank and the pump's hardware were calibrated against different rules. So the simple hole became part of a legal and technical chessboard. One tiny mechanical decision rippling into patents, compliance costs, and regional quirks. There's still one more twist. Refueling speed changed expectations. Faster fill nozzles alter internal flow rates, which changes the vacuum dynamics and can make older sensing designs unreliable. So designers added flow control geometries and safety overrides. Every time someone demanded faster fill times, engineers had to retune a mechanism designed originally around a moderate, steady flow. That trade-off, speed versus reliable auto shut, is a quiet engineering tug-of-war you feel as a short surprise at the pump. Next time you see a gas pump nozzle, don't see a simple spout. See a small machine tuned to read air, built to fail fast, and shaped by safety rules, patents, and the price of spilled fuel. See a design that chose mechanical certainty over electronic cleverness because money, law, and physics all pointed the same way. If you like understanding how the world really works, hit like and subscribe for more. Tiny hole, big rules, a clever little bit of physics doing the heavy lifting for all of us. One last practical note. When you're filling, don't block the little hole with your finger, and don't wedge the nozzle against odd angles. You'll save yourself a beep, a shutoff, or that awkward splash.